Hello everybody, and welcome back to another episode of Science with Mr. Emond. Today we're going to be continuing on in our unit on aqueous solutions in Chemistry 30, and we're going to be looking at a very special case today involving mixed solutions. When you're dealing with mixed solutions, you're going to be using your KSP in order to predict whether or not precipitation occurs. Before we get started on that, I want to go through a little bit of background. So we already know that when we are talking about the solubility of a substance, what we're referring to is the maximum concentration that substance, for example, salt, so that the highest concentration of salt in water possible in order to make a saturated solution. So when we're talking about solubility of salt, we're talking about its saturation point. When something is supersaturated, it has exceeded its saturation point, meaning there's so much salt in the water now that it can't all dissolve. You're going to have salt in the water, and solid salt in the water, I should say. And this is going to occur if the concentration exceeds the solubility point or its saturation point. And thus, a precipitate will accumulate at the bottom. So even if you have something that's fully dissolved, because maybe you did a Chem 30 lab and you heated up your beaker past its solubility point to allow extra of the solute to dissolve in the water. Well, when the temperature cools back down, that extra stuff that you forced to dissolve is no longer going to be able to stay in its aqueous state. Thus, it will have to shift, and using Le Chatelier's principle, it will have to shift to the side to reduce the amount of aqueous particles, and that will create a precipitate at the bottom. That's going to look a lot like the lab that we did in Chemistry 30, where we created crystals out of a supersaturated solution. We also know that whenever we are going to be talking about a solution in equilibrium, what we're talking about are saturated solutions. All right, let's get started. So, mixed solutions, of course, we're talking about when two solutions are mixed together. You have maybe a solution of salt and a solution of sugar, salt water and sugar water, two different ones, and we pour them into the same beaker. Well, that's mixing two solutions together. When you do that, the system is going to try to reach equilibrium. However, if the concentration of the two ions that make a precipitate is too high, then the KSP will be too great for that solution. What this means is we can then predict whether or not one of those things, either the salt or the sugar, or whatever new compound is formed by the dissolution of those compounds, maybe that precipitate will form. To do that, we calculate a trial KSP, and that's going to be the constant we would get if you mix those two solutions. And when you find that trial KSP, you can then compare it to the actual KSP for the substance, which is usually going to be given to you. Now, this might seem a little complicated right now, but I promise as we work through these problems, you're going to have a bit more understanding of what we're trying to accomplish here. So let's go through the three possible situations. The first situation is that when you find your trial KSP, it's greater than the actual KSP given to you. If that's the case, a precipitate is going to be formed. And why? That's because there's too many ions that are dissolved in the water at that specific temperature. And those ions will have to shift to either the left or the right, depending on how you set up your equation. But there's going to be a shift in equilibrium that will result in kicking the ions out of solution and forming a precipitate. The second situation, what if when we calculate our trial KSP, it is the same or equal to the KSP given to us? What does that mean? That means that we have a saturated solution. That means that we are at the point where we cannot add a single atom more, because if we did, it would be supersaturated. Or in other words, there's a perfect amount of ions present dissolved in that water. If that happens, no precipitate is going to be formed, but we're at the tipping point. That's situation 2. Situation 3, of course, the trial KSP is less than the actual KSP. And that means we have an unsaturated solution, meaning we can have more ions dissolved in that water before we hit the saturation point. If that's true, then of course that means that there's not going to be any precipitate. Why would there be? We can still dissolve more things. And there is room for more ions. All right, so let's go through actually using this now. But before we do, keep in mind dilution factors. If I am taking 200 milliliters from this beaker of salt water and 300 milliliters from this beaker in sugar water, and I'm pouring them both into a larger beaker, I now have 500 total milliliters. Did the amount of salt change? No. Did the amount of sugar change? No. But what did change? How much water they're dissolved in. We are diluting both of them. And we have to consider that dilution when we're deciding on whether or not a precipitate will form. So you have to remember how to do your dilutions. Here's our steps on how we're going to solve for these. Step 1. We're going to use our solubility table to predict if precipitates will form. How do you do that? You look to see if it says low solubility or high solubility. That's it. And you're going to write the net ionic equation for that substance and figure out what the trial KSP is. We have this stuff of potassium chromate, and we're mixing it with lead 2 nitrate. So notice I'm not worrying about the numbers right now because step 1 is just to write the net ionic equation and find out if precipitates are going to form. So that's what I'm going to do. So I have potassium chromate. Chromate is CrO4, and it's 2 minus. Potassium is 1 plus. So this is 1 plus, this is 2 minus. If I drop and swap, I'm going to have K2CrO4 1. And this is aqueous. How do I know? Because I have a solution of it, right? I don't really need to check. I know that I have a solution because I have something dissolved, right? Moles per liter. So it's aqueous. And I have lead 2 nitrate is what I'm mixing it with. So lead 2 plus and nitrate NO3 minus, which means I'm going to have Pb NO3 2. And of course, this as well is aqueous. This is going to disassociate. So this, okay, at this point, it becomes something similar to what we did in Physical Science 20, which is this is a double displacement reaction. I know that these two things are going to mix to form one of the compounds, and these two things are going to mix to form the other compounds. Double displacement. So I'm going to have KNO3, K plus and NO3 minus. I don't know what state that is. And then I'm going to have Pb, CrO4. And there are 2 plus and 2 minus. So this is just going to be Pb, CrO4. Now you have to look at a solubility table to figure out what state these two things are. So I have my solubility table here. I'm going to look at NO3, which is right there, nitrate. And with essentially all positive ions, it's soluble. So I know that KNO3 is aqueous. Now I'm going to look at chromate with lead. And this is going to be solid. All right. Let's balance our equation. So we have 1 Pb on both sides. We have 2 NO3s on the left, but only 1 on the right. So let's balance that. Now we have 2 potassiums and 2 potassiums, 1 chromate, 1 chromate. So we're balanced. I'm going to add some 1s in here because I just want it to be done. Let's go and disassociate the things that can be disassociated. So here we're going to have two K pluses, right? I'm splitting up all things that are aqueous. Two K pluses and one CrO4, 2 minus. And I'm going to have a Pb2 plus, just one of them. And I'm going to have two NO3 minuses. On this side, this is going to disassociate, so I'm going to have two K pluses and two NO3 minuses. This solid does not disassociate, so it's just going to be PbCrO4. All right, now what I can do is find my net ionic equation. So this is my total ionic equation. I want my net. So I'm going to look at what's on both sides. I have two potassiums on both sides. I have two NO3s on both sides. And that's it. I can simplify now. I like to have my solids on the left. Does it matter? Not really, because this arrow is double-sided, meaning there's a forward and a reverse reaction. I'm going to flip mine. So I'm going to have Pb CrO4, which is a solid, and I'm going to have CrO4, 2 minus, and Pb, 2 plus on the right. And these, of course, are aqueous. So from the last video, we learned how to do KSP. So our KSP for this equation, our new equation, our net ionic equation, is going to be the concentration of CrO4, 2 minus, times the concentration of Pb, 2 plus. Notice to find KSP, we didn't need all this other stuff because a lot of those ions are spectator ions. They're not actually involved in the reaction. The important one is this. And so now we have our KSP expression. Let's go back. We found our KSP expression. We have the net ionic equation. That's step one. Now, we need to calculate the dilution of both ions that will form the precipitate. And note the final volume will be the sum of the volumes of both substances. So let's figure this out. What do we need to solve the KSP? We need the concentration of this ion and that ion. Let's read what we're told. We are told that we have 25 milliliters of a 0.002 molarity of potassium chromate. Now, potassium chromate might not look like it's going to be super helpful to you, but it will be. This is potassium chromate. What do I need? I need my concentration of chromate. Well, chromate is coming from the potassium chromate, right? This thing is going to split into potassium and chromate. Let's compare the ratios, the stoichiometric ratios. We had one potassium chromate for every one chromate. What does that tell you? That tells you that the molarity of potassium chromate is going to be the same as the molarity of chromate. So it might not have looked like I knew the concentration of chromate, but I did. With a little bit of stoichiometry, you know that the initial concentration of chromate was 0.00200 molarity. Now you have to be really, really careful because that's getting diluted. I'm mixing two different solutions together. How much of this 0.002 molarity solution did I have? 25 milliliters of it. When I mixed it with this other stuff, I now no longer had 25 milliliters in my beaker. I went from 25 milliliters to 75 milliliters. But my amount of potassium chromate didn't change. It's just mixed in more water now. It got diluted. So we need to use our dilution factor to figure out what our actual new concentration is. Because this is old. This is what our concentration was when it was in 25 milliliters. It's no longer in 25 milliliters, it's in 100, 25 plus 75. To do that, we have to use our formula, the initial molarity times the initial volume is equal to the final molarity times the final volume. All right, this is my initial molarity. I know it, 0.00200. What's my initial volume? I want volume to be in liters, so it's 25 milliliters, which is 0.025 liters. Do I know my final molarity after it's been diluted? No, that's what I'm solving for. So I'm solving for final molarity. Do I know the final volume? I sure do. When I mix my 25 milliliters with my 75 milliliters, well, 25 plus 75 is, I now have 100 milliliters, which is 0.1 liters. And so I have that. What do I do now? I divide out my 100 milliliters from both sides. So these cancel out. And then I have my final concentration, right? And so my final concentration of chromate after being diluted is going to be, let's take out our calculators. We have 0.002. So 0.002 times 0.025. And we are going to divide that by 0.1. And that's going to be 5 times 10 to the 1, 2, 3, 4. All right, that's my new molarity. So I definitely want to keep this in mind. This is my new molarity, not my old one. All right, we have to do this again because we have chromate. So now we have this value. We need to find our concentration of lead. So let's go through this one more time. We have 75 milliliters of this molarity of lead to nitrate. All right. Well, let's kind of try to figure this out here. Where's my lead to nitrate? It's this. This is my lead to nitrate. My lead to nitrate turned into lead and nitrate. Which one do I care about? I only care about the lead. What are these ratios? 1 to 1. How convenient. The concentration of lead to nitrate is the same as the concentration of lead ions. They're also 1 to 1. So I don't have to change it. I just have to dilute it. Now, because we have already shown the steps there, I'm just going to skip to using this. So we're going to do it again. So my initial molarity is 0.000125. So 0.000125. This is my initial molarity of lead ions. What was my initial volume of lead ions? 75 milliliters. All right. 75 milliliters is 0.075 liters. That's going to be equal to my final molarity, which is what I'm finding, times my total new volume. And of course, when I mix them together, I have 100 milliliters. So there we go. My final molarity of Pb2 plus is, let's toss this in our calculator, 0.000125 times 0.075 divided by 0.1. All right, we want to have 2 sig figs, 3 sig figs. So 9.40 times 10 to the 1, 2, 3, 4, 5. Just going to double check sig figs up here. Yeah, it looks like everything had 3 sig figs. So we want to keep with 3 sig figs. All right, so we have our final concentration. There it is. Now we're ready to move on to the next step. So we have our 2 concentrations. What's the step 3? Use those concentrations after dilutions to find the trial KSP. So let's give this a shot. So we know that our KSP is going to be equal to the concentration of chromate and lead multiplied together. So let's go ahead and do this. So our KSP is going to be equal to 5.00 times 10 to the negative 4 multiplied by 9.40 times 10 to the negative 5. Now, I don't know about you, but I can't do that in my head. So I'm going to need a calculator. So we have 5 times 10 to the negative 4 times 9.4 times 10 to the negative 5. And that's 4.7 times 10 to the negative 8. All right, 4.7 times 10 to the negative 8. That's my KSP, my trial KSP, which sometimes you'll see this labeled as Q. Okay, that's my trial KSP. Let's go ahead and figure out what to do next. All right. Well, step 4. Compare to the actual KSP to determine whether a precipitate will form. So this is the final step. We have the KSP of lead chromate is 1.8 times 10 to the negative 14. Let's compare it to that. So we found 4.70 times 10 to the negative 8. And they're telling us that it's 1.8 times 10 to the negative 14. Is our number bigger or smaller? It's bigger. If our trial KSP or our Q value is bigger than the KSP, that means that a precipitate will form. So that's it. This is a multi-step thing, but to be honest, if I were doing this, I would not have shown quite as many steps as I did. I spread things out a little bit more just so we could demonstrate all the things required here, all the thoughts that have to go into solving a problem like this, but it doesn't need to all be written down. Only the essential steps do. So that's it. Hope you enjoyed this video, and now you know how to solve for the special case involving mixed solutions. See you next time for another video in chemistry. Bye-bye.
Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.